Welcome to the next part of the module, which continues the analysis of an example that shows how Java concurrency mechanisms can be used to synchronize and schedule the behavior of threads in a concurrent program. This part focuses on the ping-pong program implementation, building upon the design overview in the previous part. In particular, we conduct a detailed walkthrough of the pattern-oriented framework source code and show how it's customized to create and start two Java threads whose run hook methods alternate printing ping and pong on the computer console. In addition to showing how to program with Java semaphores, condition objects, and countdown latches, we demonstrate by example how the application of gang of four patterns, such as template method, strategy, and factor method, provides several benefits. For example, we show how this pattern-oriented framework makes it easy to replace the use of Java semaphores with Java condition objects to support more sophisticated behavior without changing the core ping-pong algorithm or the framework software itself. We examine a lot of design and programming concepts and source code in this video, and even though it's clean and concise, it's also heavily refactored and pattern-oriented. So it's important to read and run the code, available at this link, carefully watch this video and the previous one, perhaps multiple times, and learn how the various patterns described at the provided links work to fully understand how all the pieces fit together. Now that we've covered the design of the pattern-oriented ping-pong program, we'll analyze its implementation in detail. The bulk of the ping-pong program code is defined in the Play Ping-Pong class, which implements the runnable interface and provides a pattern-oriented framework for varying certain aspects of the ping-pong algorithm and its concurrent behavior. The Play Ping-Pong class contains several static data members shared by the threads it creates internally. These data members keep track of the number of iterations to play ping pong, the number of times to print either ping or pong during each turn, a strategy object used to portably print the ping and pong output and synchronize completion of the internal threads, and the type of synchronization mechanism to use. For example, Java semaphores or condition objects. The Play Ping-Pong constructor initializes these data members using the parameters passed to it. A static nested ping-pong thread class extends thread and plays the role of the abstract class in the template method pattern described earlier. The acquire and release abstract methods are overridden by subclasses to schedule the order of printing the ping or pong string set by the ping-pong thread constructor. The ping-pong thread run hook method executes in a separate thread and plays the role of the template method in the template method pattern. It loops for the designated number of iterations and performs the protocol that uses the acquire and release hook methods to alternate printing the ping and pong strings to the output. Several pattern-oriented aspects are shown in this run template method. First, the platform strategy print method uses the strategy pattern discussed earlier to provide a platform-independent means for writing text to the output display. Second, the acquire and release hook methods play the role of primitive operations in the template method pattern by deferring the specifics of synchronization and scheduling to the ping-pong thread subclasses. When the loop exits, the platform strategy done method is called to indicate the thread has finished its processing, which decrements the countdown latch by 1. When all running ping-pong threads have returned, the countdown latch drops to 0, which informs the Play Ping-Pong object's thread to shut down, as shown later in this video. The pattern-oriented ping-pong framework can be transparently configured to support different synchronizers, either semaphore-based or condition object-based, using the Make Ping-Pong Threads factory method covered both earlier and later in this video. We first analyzed the semaphore-based synchronizer configuration, which enables the ping and pong threads to alternate printing the ping and pong strings to the console. In this implementation, the ping-pong thread sema class extends ping-pong thread and plays the role of the concrete class in the template method pattern. It defines a 2-element array of Java semaphores that schedule the order in which its acquire and release hook methods alternate the printing of ping and pong in its superclass's run template method. The ping-pong thread sema constructor initializes this array with the semaphore parameters it receives. The ping-pong thread sema acquire and release hook methods simply forward to the acquire and release methods of the first or second semaphore stored in the semaphore array data member. These two members play the role of primitive operations in the template method pattern. They're used to decouple the core ping-pong algorithm in the ping-pong thread run hook method from the actual mechanisms that perform the synchronization. The condition object-based configuration of the ping-pong program supports more flexible behavior than the semaphore-based configuration. In particular, it uses condition objects to enable each thread to print multiple ping or pong strings consecutively during its turn. The ping-pong thread con class extends ping-pong thread and also plays the role of the concrete class in the template method pattern, just like the ping-pong thread sema class. However, it defines more data members, since its synchronization mechanism and behavior are different. These data members include a 2-element array of Java conditions that are used together with a reentrant lock to schedule the order in which its acquire and release hook methods consecutively print ping or pong in the superclass's run template method during a turn. Two other data members keep track of the thread identifiers that coordinate the passing of control between the ping and pong threads. The constructor of ping-pong thread cond initializes all these data members with the parameters passed to it. The acquire hook method of ping-pong thread cond is more complex than ping-pong thread sema. In particular, it first acquires the reentrant lock to enter the critical section and then checks to see if it's the owner of the turn, since a thread can only print ping or pong when it's the turn owner. If it's not the turn owner, it waits on the condition object, which atomically releases a lock and goes to sleep until the other thread signals it after making it the turn owner. The release method works collaboratively with acquire. When it's called by a thread, it acquires the reentrant lock to enter the critical section and then decrements the turn countdown data member by 1, which keeps track of the number of consecutive iterations per turn. This thread's turn is over when the value of turn countdown drops to 0, in which case it makes the other thread the turn owner and resets the number of iterations per turn to max turns. Finally, this thread signals the other thread that its turn can begin, and then releases the reentrant lock before returning from the critical section. Now that we've examined the pieces of the ping-pong program, we'll show how they all fit together. The run hook method of the play ping-pong class is the entry point into the ping-pong algorithm. It executes in a separate thread and informs the platform strategy that a new game is beginning. It then creates an array of ping-pong thread objects that are initialized by make ping-pong threads, which uses the factory method pattern described earlier to configure either Java semaphores or Java condition objects control how the threads alternate printing ping and pong. After this factory method returns, the ping and pong threads are started, which causes the Java virtual machine to execute their run template methods. Play ping pong run uses a countdown latch defined by the platform strategy await done method to block until both of these threads finish their processing and exit before it returns. The make ping pong threads factory method isolates the creation of the requested synchronization and scheduling mechanisms, which in this case are implemented using semaphores. In particular, we create a pair of binary semaphores, one for the ping thread and the other for the pong thread, and initialize the ping semaphore to start out unlocked. We next create two ping-pong thread sema objects, passing in the parameters. These semaphores are passed to these object constructors in opposite order to ensure the threads correctly alternate printing ping and pong. For example, the ping thread is passed the ping semaphore followed by the pong semaphore, whereas the pong thread is passed the pong semaphore followed by the ping semaphore. The main entry point method in the main class sets all the pieces in motion. It uses the factory method pattern to initialize the platform strategy object, which in this case is the console platform strategy, then initializes the command line options, which can be used to control the number of ping-pong iterations, and finally initializes the play ping-pong object with the requested parameters. When all this initialization completes, an anonymous thread is created and started to run the play ping-pong object, which triggers all the concurrent ping-pong algorithm processing discussed earlier. In summary, this video analyzed the implementation of a pattern-oriented framework that supports a family of related concurrent ping pong programs. Unlike the buggy implementation we examined in an earlier video, this framework was customized and configured with Java semaphores, condition objects, and countdown latches to correctly alternate printing ping and pong on the computer console. The use of the gang of 4 template method and factory method patterns enhance systematic reuse and flexibility by making it easy to switch between Java semaphores and condition object synchronization mechanisms without changing the framework or application software. These patterns also extended the program to transparently support more sophisticated ping pong behavior, such as allowing each thread to print multiple ping or pong strings consecutively during its turn. The use of the gang of 4 strategy pattern enhanced portability by defining a platform strategy class hierarchy that factors out different ways of printing ping and pong and coordinating the completion of printing operations on different runtime platforms, such as a Java console application versus an Android application. Although there are many classes in this framework-based solution, knowledge of the patterns that motivate and guide its design and implementation greatly simplify both understanding how it works and how to extend it to support new requirements and environments.